Well, good morning in the East and good evening in the West. We're so glad you've decided to join us as we talk today about inference time compute support for TRT-LLM. And we have two great folks to talk to you about this, both TensorRT-LLM senior engineers, Zhenhuan Chen and Fred Wei. But before we kick off, I wanted to first make sure that you know that you can join us on GitHub at the following URL. In addition, you can follow us on Discord, where we are NVIDIA developer. Lots of fun conversations going on over there, and we'd love you to join us. And then finally, we encourage you to ask questions directly as the presentation is going, and we'll answer them as we go. But if any questions come up after you've watched, you can email us directly at developercommunity@nvidia.com. And with that, gentlemen, take it away.
Okay. Hello everyone. I'm Fred. I'm very glad to have the opportunity to introduce to you today the work of TensorRT-LLM team in inference time compute. Today's content is divided into four parts. Firstly, I will introduce the background and the importance of inference time compute, and from the system level and the perspective of TensorRT-LLM. What contribution we hope to make to the application of inference time compute. Next, I will explain the design concept, core features, and the implementation of our work called scaffolding. Scaffolding is a framework designed for inference time compute, and I will demonstrate and explain scaffolding's core code to everyone. Then Zhenhuan will demonstrate through an interesting example to show how an inference time compute algorithm can be quickly implemented through scaffolding. The algorithm is Dynasor-CoT, which proposed by the team from UCSD. It can reduce the number of output tokens for difficult problems. This example demonstrates how to implement an algorithm and scaffolding and highlights the advantage of scaffolding. Finally, I will introduce some future work scaffolding to everyone. Okay, let's move to the part one. Inference time compute can also be referred to as test time compute. For the sake of the consistency, I will use the term inference time compute today. Broadly speaking, any computation during the model inference can be called as inference time compute. However, this concept was truly proposed and gained attention only after the emergence of inference of reasoning models such as O1 and DeepSeek-R1. It was discovered that using more compute resource during the inference stage might significantly enhance the model's capability. Therefore, the method of using more compute resource during the inference stage to achieve better results is generally called as inference time compute. So why is inference compute important? The scaling law is very important rule that describes the development of AI. We show that the core issue of AI development is how to transfer more compute results into the terrain of the models. The pre-training, post-training, and inference stage are three parts of scaling law. From the sequence of technology development, the scaling law of pre-training was discovered earliest and have been explored most thoroughly. The scaling law of post-training has also developed with the development of reinforcement learning this year. The development of inference stage is relatively late, but within the arrival of the agentic array, the scaling law of the inference stage will enter a period of rapid development. And more studies and work have proved that the inference-time compute can remarkably enhance the capability of AI. The figure on the left shows that, together with an effective verifier, more rollout times can increase the success rate of the final task. The figure on the right shows that, after using the method of inference-time compute, then 7 billion small models can even achieve the same or even better levels as the hundreds of billion large model and specific tasks. So, what are the ways to achieve the scaling of inference-time compute? The first approach is increase the length of output seconds. The paper on DeepSeek R1 proved this to us. However, how to make the inference framework support long output sequence is not what we are going to share today. This is a basic feature of the inference framework. However, what we still need to pay attention is that it may not be cost-effective to generate long output sequence without any restriction. Therefore, some algorithms have emerged to determine when the request should be early terminated. The Dynasor-CoT is an example of this algorithm, and we will introduce it later. The second one to achieve inference-time compute is external methods. The most classic algorithms are best of n and majority voting. They sample the same point multiple times. That is, make the multiply inference request and get the multiply response. The majority voting algorithm will return the answer that appears most frequently among multiply response. Best of n introduce an evaluator to score multiply responses and returns the one with the highest score. This evaluator might be an external tool or another LLM. More complex algorithms are tree search algorithms. Monte Carlo trees are commonly used data structure. This algorithm sampling multiple times for each step of the problem, score the intermediate results of each one, and then decide to proceed to the next try. How to better implement this method is the main problem we want to resolve today. It should be noted there are great many variations of this method, which means that the engineer usually need to implement a new algorithm. And we also noticed that the agent is now one of the topics that everyone cares about, especially multi-agent. The picture shows a common multi-agent architecture. The planner agent sends tasks to the executor agents. After the tasks are completed, the result is sent back to the planner agent, which then determines whether to proceed to the next round of operation and tasks. If we think carefully, we will find that that is eventually also a kind of tree search. The sub-agent extends the leaf node, and the planning agent evaluates the leaf nodes and decide the next step behavior. The multi-agent just require more context engineering and external tool costs. So if we implement a framework that we can score the methods such as best of n and Monte Carlo tree well, then this framework should also be able to support the multi-agent architecture well. Let's think further. If we want to implement a framework to support this inference-time compute method well, what are the core requirements? First of all, it must be able to easily implement these methods, which is very important for the rapid iteration of technology. Secondly, it can offer good performance. For this method of inference-time compute, the key to achieve good performance is to execute tasks in parallel as much as possible. For example, for the best of n method, multiply sampling can be executed currently. Thirdly, the backend that perform tasks such as inference engine and tool service should be able to switch flexible. Finally, the code should be modular and reusable. Okay, may I ask if anyone has any question about the background part? Okay, if anyone have question, Zhenhuan can interpret me and we can answer the question.
There's no question about this presentation, but question about TensorRT-LLM. We support torch backend now, and it doesn't need to compare, so you can just to try to our new backend. Thanks.
Okay. I think we can just go step to the next part first, and maybe this question can be resolved. Yes. Okay. So let's move to the design and implementation section. Okay. To meet these requirements, we design and implementation implemented scaffolding, which is a framework that can be used to develop various inference-time compute methods, such as best of n or modularity. Yes, what we mentioned above. It has three core features. The first feature is decoupling inference-time compute method and execution backend. This enables engineers in charge of algorithms to focus on the design of the methods and the workflows, while the engineering responsible for deployment can flexibly switch various backends to try to find a better deployment solution. The second feature is to make the inference-time compute method modular and reusable. This is very important for the software project. The project may include various inference-time compute methods. This makes the project maintainable, and the implementation of the new variants will be easy. The third feature is provide sufficient concurrencies to achieve good performance while ease of use. Concurrency often brings complex async scaling and make the implementation difficult, but we still hope to find a way to achieve the concurrency with easy of use. Scaffolding consists of three core components. Let's first briefly introduce these components. The worker class is the backend that executes a single task, such as sending an inference request to an LLM inference framework or service, or completing a tool call to any external tool. The controller class focuses on defining the workflow of inference-time compute methods. The scaffolding, and finally, the scaffolding LLM class is responsible for integrating the worker and the controller and completing the entire task or the entire workflow. Okay, let's understand the relationship between them more clearly through this figure. The user passes the prompt to the scaffolding LLM, and the scaffolding LLM will pass the prompt to the controller. The controller starts to execute the predefined workflow. When the workflow needs to call the LLM inference or external tools or any other operation, the controller creates a task and passes it to the scaffolding LLM. The scaffolding LLM then forwards the task to the corresponding worker. After the worker completes the task, it will write the result into the result field and the scaffolding LLM will pass it back to the controller. After the controller receives the completed task, it will continue to execute the workflow and repeat the process of sending and complete the task until the inter workflow is completed. The final result is returned to the user by scaffolding LLM. Here we can focus on 2 points. First, scaffolding LLM provides users with interfaces. Second, the controller does not directly call the worker. Okay, let me further explain how the 3 core features are implemented. The first is the decoupling of the inference-time compute method from the backend. Okay, let's take a look at the code of the worker. This is very easy to understand. Its code interface is run task. This function takes in task as the parameter. Then complete this task and write the result into the corresponding field. It should be known that run task is an async function, and it can be concurrently and asynchronously called within Python async IO. Next, let's take a look at the core code of the controller. Here begins the unique aspect of scaffolding. It is a bit more complex than the workers. It has 2 core interfaces. They are generate and process. Generate is the entry point for the scaffolding LLM to invoke. In the default implementation of generate, it produces a task and then invoke the process function. The process function is the most important part of every controller class, as it defines the implementation, the workflow of this inference-time compute method. So let's go into a specified subclass of controller to see how process is implemented. Essentially, a process is a iterator in Python that can return a list of tasks using build statement. When the iterator is re-entered, that is, when the build statement ends, the task has been completed. That means the result of task has been written into its result field. Then the process can proceed to the next step. This example is relatively simple, so it returns directly. So we can see that the process function of controller can focus on the design of the workflow. It does not directly call the worker and does not need to care about how these tasks are completed. Yes, it just needs to focus on the logic of workflow. So we then need something that can combine the controller and the worker together. That is the scaffolding LLM class. This code shows that how a user creates and uses the scaffolding LLM class to complete the entire workflow. Users need to first create the instance of worker and controller, and use them to create the scaffolding LLM class. Then call the generate interfaces of scaffolding LLM to get the final result. Okay, yes. Here we have explained how the decoupling of inference-time compute method in the backend. Yes, we have explained how this decoupling is implemented. Okay, so let's move to the next feature. Okay, next, let me take a look at how modularization is implemented. Through the above description, everyone may have a deeper understanding of scaffolding, so the following part will be easier. The modular implementation only requires the subcontroller to be a member of class, and then the process function of subcontroller is called using the if-from statement. Yes. By the same way, once a controller is implemented, it can also serve as a class member of another controller as a subcontroller. Yes. In this way, we can organize the various inference-time compute methods together in a modular manner. For example, if you have a controller as a reward controller, yeah, you can use this reward controller in best of n in Monte Carlo tree search. Yes. So you are no need to implement the reward logic many times. Okay, next, let's take a look at how users can achieve surfaces concurrencies using scaffolding. We hope to make this as simple as possible for users. We have implemented 3 levels of concurrencies to meet the needs of users. At the scaffolding LLM level, we offer the async interfaces, allowing the developer to achieve concurrencies between different scaffolding LLM requests within Python async IO. The second level is concurrency at the subcontroller level. The code is the majority voting controller. Yes, we use it as an example. This controller create n subcontroller for n sampling. We can call the process function of this subcontroller one by one, but this is not performance friendly. The cost of this subcontroller can be concurrent because they do not affect each other. So we provide a helper class parallel process to the development. The development only needs to put this subclass and the parameters of the process into a list, and then give the list to the parallel process and just use the parallel process as the code shows. And then the multiply subcontrollers can be go through concurrency. The third level is the concurrency at the task level. Each time the multiply tasks are built out, they can be executed currently, even if they are sent to the same worker. The combination of these 3 levels can enable the entire service of the user to achieve sufficient concurrency. And we have also made effort to ensure the easy of use as you see. Okay. At this point, we can make a summary for the overall implementation of scaffolding. The question we want to answer here is that after we have provided the infrastructure, which part do user still need to customize and develop? The answer is that if user want to implement new inference-time compute methods, user can just develop a new controllers. They can in these new controllers, user can also call an existing controller as its subcontroller. If user want to implement a new backend, yes, such as user want to use a new LLM inference engines, user can either create a new worker to add a new task handler, or add a new task handler to a existing worker. Okay. As for scaffolding LLM class, we have hidden many complex implementation to the scaffolding LLM class, such as async scaling, such as anything difficult. So the users do not need to modify the code of the Scaffolding LLM class. Yes, the user just need to focus on the controller or the worker. In the controller and workers is easy of use to modify or customers to a new method or anything other. Okay, all those users can customize their own controllers or workers and tasks. We have still implement a series of most commonly used ones as the foundation. In terms of workers, we have implemented the TRT-LLM workers. Yes, we use the TensorRT-LLM as a LLM inference agent to do the inference. And OpenAI API workers. Yes, it can just user provide the API key and then the URLs, and then the worker can do the inference. And we also implement the NCP worker and use this worker to development the external tool calls. Yes. In the terms of the task, we have generation task, reward task, and tool call task. In the controller, about controller, we have development majority voting controller, best of n controller, and reward controller. We not development the reward controller as PRM, which means process reward model. PRM reward controller. Yes, they are the foundation, and user can customize their own inference time compute method. Yes, this is the part. Yes, does anyone have any questions?
Here is a general question about our background from Grace. She said, from a practical standpoint, how do you think organizations should decide where to invest their resources? In training larger models or in building infrastructures to maximize test time scaling?
Okay, I think both of them are important. Both of them are the important way to get the AGI or the good AI abilities. They are and it is a good question to think about what we should assign the compute resource to these two paths. Yes, I think it's not it if you not have a same question in any regions. Yes, such as for the some problems such as math or such of codings, we have discovered many good methods in the inference and compute, and so in these problems we can try to we can try to allocate more compute resource to the inference and compute. Yes, I think it depends on the specific problem or specific service you want to resolve or you want to provide. Yes.
In summary, I think training is quite resource consuming, and if you just want some specific area problem, you can use inference time compute to solve this small area problem. And yeah, I think it's a new increased point besides training. Okay, hope answer your question. There's another question from the bar. How do we mathematically balance exploration with exploitation when controllers decide between multiple possible worker strategies?
Okay, John, can you answer this question?
Okay. I think maybe you misunderstand our controller's meaning. We can have multiple workers in the controller, and it's decided totally by users. We don't do any exploration or exploitation in controller. We can design algorithm in controller to decide which task to do for which worker. Like you can do exploration for one worker and do exploitation for another worker. Yeah, it's all.
Okay. Thank you, Zhenhuan. Yes, from my side, I would like to put as many logic operation in the controller. Yes, the logic operation such as the such as do the majority voting, and such as prompt engineering. Yes, the logic is compressed, but the operation is will not do not need heavy computer resource. Yes, this part I would like to put them in the controller, and the workers I would like to use them to complete the heavy operation. Yes, such as the LLM inference. Yes, it is heavy. It will need a minute. It will need nanometers or long. Yes, or the two cores, and the external two cores is also heavily. So this part is heavily, but the logic is easy. So this part can be rewritten in the worker, and this part can be easily reused in the controller. Yes. So this is my opinion.
There's another question from Aaron. What concrete advantages does your scaffolding framework deliver over existing ITC frameworks in throughput, latency, and ease of implementing methods like best of N and MCTS?
Okay. Yes, we have do some experimentations, and it shows that scaffolding can get services concurrencies to get good performance. And as for other framework such as the agent framework, some of them can also get a good performance, but the code is difficult to read. And as we have mentioned about the async scaling made the code difficult to read. And some of them the code is easy, but the async is not sufficient. The advantage of scaffolding is to get both the goals of this. Yes, it can give sufficient concurrencies, and it is easy of use, and we give the user to do the to represent the concurrent scaling as much as easy as much. Yes, I think this is the advantage of scaffolding.
Okay, thanks everyone. We can move to the next part.
Okay, the following part will be and this part will be introduced to everyone by Zhenhuan. Yes.
Okay, thanks, Brad. Hi everyone. I'm going to introduce a practical example how to integrate a complex inference-time computer algorithm into scaffolding. In this example, we collaborated with the Dynasor team from UCSD, helping them contribute their latest research to our framework. Next page. First, let's check out the Dynasor demonstration in the right picture. It presents a side-by-side comparison of baseline model and enhanced output with Dynasor-CoT. The prompt is a simple algebraic problem in the bottom. And the left one output is from a standard LLM with a full CoT process to solve the problem. Many of the sort process are not necessary. And the right one is much cleaner. Its sort process very short and gets the final answer very quickly. We can see that the final speed up is 5.74x. And the Dynasor helps to save a lot of tokens. So, and let's see how it can be integrated into scaffolding. Next page. Okay. First, let me briefly introduce Dynasor's algorithm. It's a certainty-based early stopping technique for CoT model, and it doesn't need to load extra model and it doesn't need extra training. It's a pure inference time technique. In the right picture, we can see 3 common cases. For the top, the math problem, we can say for case 1, after several tokens output, it will insert an extra probe generation request to try to get early stage result, which is represented by a robot icon. Specifically, it will append a sentence like, "Oh, I certainly got the answer to the whole problem," and like it's printed in the bottom in red words. And so the model will try to generate and the answer directly into the special box format. In case 1, for 3 probe requests, we can see all the answers is the same 3159, so that we can assume it's the final answer with high certainty. In case 2, we will get 3 different answers, so we need to continue further generation. In case 3, similar to case 2, but we find special tokens like wait, and but, which indicate the hesitation of a model. So we will also continue further generation. In summary, if the probe request continue to get the same result, it can terminate the process early and avoid unnecessary computation to speed up inference. Okay, let's see how to implement it in scaffolding. Next page. First, we just need to implement the controller class. We just need to inherit the controller base class and add some init arguments like certainty threshold, which means how many equal results we need to see so we can terminate the process. Its by default is 3. And the chunk size means the interval to insert a probe request. And uncertain words, a list of words that indicate the hesitation. And the probe suffix, the prompt to get final answer in probe request. And answer suffix, the actual tokens in output string. And tokenizer, we need a tokenizer to encode and decode string during the process. Next page. Okay, it's a process function. Firstly, we need to construct 2 generation tasks. One is for normal generation. We call it proposal task, and its max tokens is chunk size, which means we can stop and say whether we need to continue. Another task is the probe task. We set the max token to 20 for quick return. Next page. This part is the main for loop. We will process the generation tasks with an iterative approach. Every iteration, we will append probe suffix to current prompt and set it as probe task's input. Then we add two tasks and wait for the results. It will be handled properly by Scaffolding LLM and workers. Next, we will extract the answer from probe task's output. There needs a lot of detailed logic to process the stream, and we'll skip this part. Then, with all historical probe tests and answers, we can decide whether to continue the next generation in should_early_stop function. Like I just said, it will say how many the same answers we get until now. If the responses is consistent, it will trigger early stop. If it early stops, it will combine answer suffix with current prompt to get the final answer. And if not, current prompt will be appended with proposer's output and continue next generation. But you can hit the hide button. Maybe it's
okay. You made this.
Yeah. Hide that. Okay, thanks. And notice that for each iteration, we will append the output string to current prompt, so it will be longer and longer, but it will be optimized in TensorRT-LLM because it supports KV cache reuse. So we will not do duplicate computation for previous prompt until it's another evidence that the design is modular and reusable. Next page, please. Okay, let's see the example to use this customer Dynasor controller. Like previous Fred is showing, we need to construct a TRT-LLM worker. Here is a TRT-LLM worker. And then a Dynasor generation controller we just implemented. And here, if you want, you can directly stack a majority vote controller above it to enhance the ability. Then we give the controller and the worker to the Scaffolding LLM and call the LLM.generate to get results. When I say the interface is very clean and easy to use. Next page. Okay, this slide I will introduce an example that during our development of scaffolding, we find some cases can feedback into TRT-LLM. For example, if we run a batch of 5 prompts with the same 4K tokens, because they are all in the same batch, the later prompts cannot directly reuse the first prompt's KV cache and cause it duplicate computation. In the above picture, we can see the later 4 prompts all need to compute 4K context tokens. And we found this problem and add a new feature to support in-batch KV cache reuse. In the bottom picture, after we fix the problem, number of context tokens become to 1 for the later 4 prompts, and it speed up the inference. Okay, that's the end of my part. Let's move to Fred.
Okay.
Any questions?
Yeah. Any questions for this part?
I think we can go to the future part, future work.
Okay. Thank you, Zhenhuan. Yes, let me go to the future work. Okay. First of all, what I want to say is that our work has been fully open sourced in the TensorRT-LLM project on the GitHub. Almost all of our work has created issues on GitHub, and we welcome everyone to join us in the community. Yes, the future work is divided into two parts. The first path is to enable scaffolding to support more inference-time compute methods, especially the methods of agentic, which is the example we want to have at present. Yes, we plan to implement an open source multi-agent based method for the popular application like deep research. Yes, this is a multi-agent based workflow. Yes, of course, the best of n based on new reward methods and various new Monte Carlo tree approach are also required for the implementation. Yeah, this is the first part. The second part is more interesting. The second part is that we how to find more opportunity to optimize TensorRT-LLM based on scaffolding workloads. Yes, from the size of the TensorRT-LLM teams, we want to get more feedback from the workload side. Yes, including the inference compute method workflow, the agent workloads. Yes, nowadays the agents generally use LLM inference framework as a black box, which might miss some opportunities. For example, in terms of KV cache reuse, scaffolding can identify which paths are system pawns and which paths are likely to be reused in the subsequent requests of this agent task, and which path cannot be reused and can be evicted immediately. This information can make the reuse of KV cache more effective. For batch scaling, multiply inference requests of majority voting should wait together or be complete at the same time, because the latencies of users to get the final result depends on the completion of the last inference request. Yes, so some of them is completed and some of them are pending. It means the users needs to wait more times. Yes, we believe that there are more optimization opportunity here than what we have thought of, and the opportunity we have already thought of also more than the human resource we can currently invest. So once again, we welcome and look forward to more people joining our open source communities. Yes, you can find these issues in the TensorRT-LLM GitHub issues with the scaffolding tag. Yes, I also give the link in the slides. Yes. Yes, that's all we share today. Yes, thank you all for watching. Okay, let's move into the answer the question stage. Yes, feel free to ask any question. Yes, hi Zhenhuan, is there any question?
There is a question from user, and if we have two workers to generate better results, which solution is better? Two same models or two different models?
Okay. I think if you use the TRT-LLM workers, I suggest you to use two workers, and one for the big models and one for the one for the small model. And OpenAI API worker, yes, it's the same, because the workers can manage the resource of the LM inference engine. So in this case, I will suggest you to development two workers, And I have yes. Let me find the code. Yes, 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 you can see the code. We have the worker tag here. Yes, you can set the worker tag in the controller code, and in the creation of the scaffolding LM, you can map the worker tag to the instance of worker. Yes, if you have worker, yes, you can make two worker and this map. Yes, and then the scaffolding LM will dispatch the task to the corresponding workers. Yes. Hope it can help you.
Okay. There is another question from LinkedIn. What concurrency guarantees does scaffolding provide across the three levels? LM request subcontroller task these three levels, and how do you handle back pressure, retries, and failure isolation?
Okay. Yes. The first case, the error handle is need to the error handle is need to optimize is need to more optimize. Yes. Now we will fall back the error stature at the API of the scaffolding LLM. Yes. Yeah. It will give expectation exceptions throughout. Yes. And for the three-level concurrencies, yes, this level is this level is controlled by the Python async IO. Yes, and these two levels and the two level essentially it's also controlled in Python async IO. Yeah. So you cannot give any assumption about the sequence of the task which is executed. Yes, if you made them concurrency. Yes, I'm not sure if I get the right question you want to you yeah, yes you want to. Yeah, Zhenhuan can help me to supplement.
Okay. I think it's the right answer. I want to answer. There's another question. We use a PRM reward as a controller. Are you essentially evaluating intermediate steps in a Bayesian learning fashion, or is it functionally similar to RLHF, where you optimize against a learned preference model? Maybe I can answer this question.
Yeah, I think it's
Okay.
algorithm level. I think it's a algorithm level question. For the reward algorithm, in fact, PRM reward is not the most popular reward algorithm now. Yes, here there are many reward algorithms as I know, such as the LMS judge. Yes, is so much algorithm. So we do actually need more reward controller here. Yes, but here I cannot comment which one is better. And from the side of scaffolding LM, we hope we can get more. We can support more reward algorithm. Yes.
Well.
All right. Well, thank you all so much for participating in this event. Want to give special thanks to Fred and Zhenhuan for taking the time to inform everyone about TensorRT-LLM and to answer all of these questions that we've had. Great questions, by the way, from the audience. So if you have more, we did provide the email address that you can send them to, and would love to read those. But otherwise, please do keep track of future events for TensorRT-LLM. We will have more live streams coming in the near future. And thanks again for joining us.
Thanks.
Thank you.